Hey guys, Miss Miklos here, and today we are going to be talking about how to deal with graphs of functions. And so a lot of the concepts that we're talking about are similar to things we've already discussed, except this time, instead of focusing on looking at an equation or a set of ordered pairs, we're actually focusing on a graph. So if we look at this first set of directions, it tells us to find the domain and the range. I told you guys earlier that domain and range are going to be really important, and this is going to show that I was telling the truth, okay? Really important stuff for us to know. So we need to remember that domain is talking about all of the x values, and the range is talking about all of the y values. And some important things for us to remember is that when we're looking at the domain, if we're looking at the x values, we're looking from the very left to the very right. So we're going to move from left to right. This means that our smallest value will come first. When we're talking about y values, the smallest value will also go first. So this time we're going from down to up. So we're going to go from down and then look up. We will also be utilizing interval notation, which we learned last lesson. And just a reminder, we use parentheses with interval notation when a value is not included. So if we're looking at a graph, that might be something like an arrow that's going to infinity or an open circle or something like that. When we have brackets, that means that value is included. So that would be a solid point on a particular graph. So let's get into this very first graph here. So we're going to start by talking about what we think the domain is. So if I'm going from left to right, I notice that this point over here looks like it's the very left-handed point. It also, I notice that there's not an arrow. It is not continuing to the edge of the graph, which also indicates that it continues forever. And it looks like it is a close point. So if I look at this graph, it looks like that x value is -1, -2, -3. So since it is a close point, I'm going to put a bracket. And I notice that this continuously hits every single x value until we hit the furthest right-hand x value, which is down here. I notice that automatically this is a open circle, which means that we're going to have to use a parenthesis. And if I look, the biggest x value there would be at 1, 2, 3, 4. So I'm going to say that our domain is from -3 to 4. It includes -3, but it does not include 4. Now with our range, we're going to do something similar. This time I'm going to go down, up. And the lowest point on our graph looks like it's right here. And that looks like that is at a y value of -1, 2, 3, 4, 5. And I notice that this is a solid line, a solid point right there. So that means that I'm going to use a bracket and say that it is -5. And it continues all the way up until this point right here. This is the highest that our graph is. And that looks like it's at a y value of 1. And this is a solid point as well. So I'm going to say that our range is from -5 to 1, including both -5 and 1. Now, some of you guys might be a little bit confused because we have this open circle. But if we look to the left here, there is actually a close point right where that circle is. So that is why that particular y value is included in the domain. Looking at our next problem here, if I'm trying to go ahead and find our domain first, I notice that when I move from left to right, I see these arrows. And arrows means that this function continues in this direction and that direction. So what this means is that it continues all the way to -infinity. And we spoke last class that whenever we have negative infinity or positive infinity, it's kind of it's an abstract number We don't actually reach that number, so that's why we use a parenthesis, because we don't include negative infinity. This is just telling me that it's all the values leading up to negative infinity. As we move along, I notice that the furthest point to the right also has an arrow. So we are going to say that our domain is from negative infinity to infinity. Now our range, when I start down below, I notice that there's nothing going down here. The very first y value I notice is at y equals 0. And this is a closed point, so I'm going to put a bracket and say 0. And as I move up, I notice the highest points here have arrows on them. And even though these arrows look like they're going to the right and they look like they're going to the left, I think we would all agree they're also going up. So that means that they are going all the way up to positive infinity. Our next graph here looks kind of weird because if we're looking at the domain from left to right, I notice that there's this giant gap here where no values exist. So we're actually going to break this up into two different pieces. So this is like our first piece, and this is like the second piece. So if I'm talking about the domain, from the left, I notice that there are arrows. So we're going to say that it's from negative infinity until we hit an x value of negative 3. Negative 3 has a bracket because that is on a solid line. Now if we look at the second portion here, it looks like there's this break from negative 3 up until we hit 3. So I'm going to say 3, and once again I used a bracket because it is a solid line. And I notice that these arrows mean that it's continuing forever, so I'm going to say it's going from 3 to infinity. Now, just like we talked about last class, when I'm combining two different domains together, or two different things together in interval notation, I'm going to use the union symbol to connect them. Now, with our range, notice with our range going up, down, and then up, it's pretty continuous. Even though these are separate parts of the graph, there's not a y value on this graph that has a big space in it because these arrows mean that it's continuing down and these arrows mean that it's continuing up. So our range is going to be from negative infinity to positive infinity. The next thing we're going to do with graphs is utilize the vertical line test, and that is one of the tests we talked about the other day that lets us know if something is a function. You guys learned this in Algebra 2, but this is just a good review for us. So, if I have a vertical line, here we go, I'm going to go straight across, and if at any point in time my vertical line is touching more than one point, we would say it is not a function. In this case, it looks like at every single point I'm only touching it once. So we would say yes, it is a function. Now if we look at our next one, as I go along here, we have some major problems because as I can see at this point, I'm not touching 1, I'm not touching 2, but 3 different points at the same x value. Remember, we said that an x value, or a function, means that each x value only has one y value. So this is why our vertical line test is failing. So we would go ahead and say not a function. And I wouldn't be really picky about the way that you wrote that. It's just important to indicate, yes, I know it's a function. No, I know it's not a function. Now we're going to explore graphs and talk about what we call increasing, decreasing, and constant intervals. And the big thing that I want you guys to remember from this is that we are going to always be talking about the domain. So when we're assigning values to each of these categories, we're really used to seeing a graph and thinking about ordered pairs. Instead of thinking about ordered pairs, we are thinking about the domain. We're only thinking about the x values. Since we are only talking about the x values, the question we're really asking ourselves is what is happening from left to right? And as we look through different graphs, we'll see sometimes one thing's happening the whole time. Sometimes multiple things are going on, but I'm always viewing my graph from left to right. So if we look at this first graph, I really notice it looks like there's 3 different parts to this graph depending on what's occurring from left to right, and I'm going to go ahead and circle them. The first part, I'm going to start at the left here, and I notice that this whole section looks like it's doing the same thing. Then there's a second section that looks like it really is staying the same, it's constant. And then there's a third section where we see that change happen once again. So what this tells me is that I'm going to be writing the domain for 3 different times. So if we take a look at this first part, from left to right, it appears as if it is decreasing because it is going down from left to right. So I'm going to say that it's decreasing starting at an x value of -1, -2, -3, -4. And if I'm looking, it looks like this is the point where it changes from decreasing into something else. And this brings up something that's interesting. Often it will talk about open intervals. And we've talked previously about interval notation. We always use a bracket when we want to include something. The difference this time is it's difficult for me to know at x equals 0, is that included in this portion of the graph, or is that included in this portion of the graph? So what we end up doing, we end up using open intervals, which means use a parenthesis, and that's just saying that everything leading up to 0 is decreasing. Now, as soon as we get into this second part, it looks like it is constant. Okay, it is not rising, it is not falling. And being constant starts at 0 and it goes to 1, 2, 3. And once again, I'm using those open intervals because those are the places at x equals 0 and x equals 3 that the change is happening. Once again, I just want to point out all of these values that I'm writing are all the x values of these important points. As soon as we hit x equals 3, we notice something else changes and all of a sudden it is rising from left to right. So we would say it's increasing from 3. And what makes this one look kind of strange is that it goes all the way to the edge of the graph. And what we will see when things go all the way to the edge of the graph, it is like it has an arrow attached to it. And we read a lot of things off the graphing calculator, and the graphing calculator does not show an arrow. So we're going to say this is increasing from 3 all the way until we hit infinity. If it clearly had stopped somewhere and we knew that it was not going to infinity, then we would go ahead and put the x value of that end point. We would use a bracket if it was a closed point, and we would use a parenthesis if it were an open circle. If we look at this next one, once again, it looks like there are 3 distinct parts. Okay, and I'm going to go ahead and circle them once again. This one actually looks really similar to our previous problem, but we notice that we can see that there are arrows on both of those parts. So I just went ahead and wrote out those 3 labels, and as we start, and this can be tricky at times, even though the arrow appears to be going up, remember we are reading it from left to right. From left to right, it is decreasing. So we're going to go ahead and say this is decreasing from negative infinity until we hit -1. So negative infinity, I know it's going forever this way, but from left to right, here we go, from the left to right it is still decreasing. As soon as I hit -1, it is constant until we hit 1, 2, 3. So I'm going to say it is constant from -1 to 3, and then it is increasing from 3 to infinity. If we take a look at this next graph, it looks like the same thing is happening over the entire domain. Okay, from left to right, it only appears to me as if it is increasing. So we would say it is increasing from negative infinity to positive infinity. Here's another one that has a lot of stuff going on. Okay, once again, I'm just going to kind of circle the different portions here. And as we start from the left, it looks like it is rising from left to right. Once again, remember, we don't care about the arrow, we care about what's actually happening from left to right. Now, as soon as we hit -1, all of a sudden it starts decreasing until we hit an x value of +1. So I'm going to write decreasing from -1 to +1. I'm using my parentheses because I am saying all the values leading up to -1 and leading up to +1 are decreasing. And then this last little piece, once again, looks like it is increasing. And we've learned when we have more than one section that is doing the same thing, we are going to use the union symbol. So I'm going to say from 1 to infinity is also increasing. Looking at this next graph, to me this time, it really looks as if there are only two different things that are going on. As soon as I start from the left, it appears to be increasing from left to right. Since there's an arrow, we know we're going to use -infinity. And it looks like it goes to an x value of 0. So I wrote that it was increasing from -infinity to 0. As soon as we hit 0, something else happens and it starts to decrease from left to right. So I'm going to say it is decreasing from 0 to +infinity. And here's our last example of this type of problem. And once again, it looks to me like it's in 3 different pieces. I'm going to break those up for us once again. And as soon as we start, even though this arrow, remember, we're throwing it away, from left to right, this is increasing. So I'm writing increasing from -infinity until 0. Now, as soon as I hit 0, something else happens, and it looks like it is constant. And it appears to be constant from 0 until we hit 3. Because the x value of 0 and an x value of 3 is where that particular domain is. As soon as we hit 3, it changes once again, and this time it is decreasing from 3 to +infinity. So once again, I actually think finding the intervals of increasing, decreasing, and constant is very straightforward. The thing I need to remember is that we are talking about the x values. The next thing we're going to look at graphs is talking about the relative minimums and maximums. And earlier this week, we already learned how to do that in our graphing calculator. So I just really want to focus on how our mins and maxes connected to what we're doing today. So I'm going to go ahead and graph these pretty quickly and easily for us. So when I graphed this, this is what we got. And we've said that relative mins, that is the lowest point in an area where it's rising on both sides, and a relative maximum is the highest point where it's decreasing on both sides. And the thing that I want to point out, okay, I'm just going to draw here. Okay, those look like relative mins to me, and this looks like a relative max. And if we actually went ahead and split up what this graph was doing from left to right, just going to circle the different pieces here. And we might notice that all of the pieces of increasing, decreasing, and constant, when it's split up into those intervals, is separated by either a relative min or a relative max. So, for example, if it was given to me that this point here was at -2, I don't know why I said negative, that would be positive. +2, let's say it's like 1, 2, 3, 4, 5, 6, 7. -7, for example. And let's say this point here was at 0, -1. We could say that this piece is decreasing from 0 to 2. So if relative mins and relative maxes are given to us, it makes finding intervals where something is increasing or decreasing very, very simple and very easy to do. And here's the graph for our next one. And okay, there is the lowest point. That would be our relative minimum. And once again, we can see that the min splits it into 2 parts. The other thing that I just want to quickly stress about relative mins and maxes is that the maximum number of relative mins and maxes is always the degree minus 1, so it's 1 less than the degree. Just a reminder, the degree is the highest exponent on any particular equation. So, for example, here the highest exponent was 4, and would you believe it? We have 3 relative extrema. Extrema is what we say when we combine mins and maxes together. Our second graph here, our highest power, our degree is 2, so it would make sense that we only have 1 relative minimum. The final thing that we're going to talk about is this concept of even and odd functions. And there's a few different things that we'll talk about regarding those classifications. So something is even if it is symmetric around the y-axis. And another thing that we may need to look at if we're trying to prove it using points is that f of x is the same as f of negative x. And what this really means is that the y values, the outputs, will be the same for x values of opposite values. So f of 2 and f of negative 2 would give us the same output. Visually, here's a picture of what this would look like. Okay, we can see it's symmetric around the y-axis. If I fold on this line, it would look exactly the same, other than the fact that graphing isn't super great in this app, but that's okay. The other really quick thing that we can use to help us out is that all exponents are going to be even, and having a constant is okay. So some different cases, if they gave me a graph, I would probably want to use ordered pairs to prove it using this method. If it's just asking me real quickly, is it even, is it odd, I might just look at the equation and see, oh, everything is even, so it's an even function, or it's not, so then it would not be an even function. If something is an odd function, it is symmetric about the origin, and we will see f of negative x is the opposite of f of x. So we saw in an even function, these two values are equal. Here, one is the opposite of another. So this is what an odd function would look like, where I can see it's symmetric here. So things that are in quadrant 1 are also in quadrant 3. Things that are in quadrant 2 would also have to be then in quadrant 4. Another way that we can see is if all the exponents are odd, and in this case there can be no constant, and we'll learn later on this chapter why something that has a constant would not be symmetric about the origin. So let's quickly determine if things are even, odd, or neither. If we look at this very first equation, I notice the exponents are all even. This constant is fine, so we would say that this is even. There we go, even. Okay, our second one, I see my exponents are 5, 3, and 1. So this would be an odd function. Our next one, we have 3 and we have 1, so that would be odd. And our final one, we have 3 and 2. So we're going to say that that is neither, because it has a mix of odd exponents and even exponents. Okay, so this is a quick way that we can just look at an equation and tell if it's asking us to prove it or if it gives us a graph. We would need to use the f of x method of seeing if it was even or odd. So hopefully you guys are feeling a little bit better on graphs of functions, and we are going to continue using them for this entire year.